Welcome to Lesson 23, Math 221, Calculus 1 marches on. We have derivatives in our toolbox. It is time to look at how to use the derivative in a geometric setting. I'm going to present 4 classic examples in this screencast. They follow the same basic recipe. If you learn the recipe, you can do the problems, usually assuming you know the geometry. They are questions like this one. Take a moment and read it. So we talk about geometric contexts. What does that mean? Well, that means we're probably going to draw something. In this case, we're probably going to draw, a rectangle. And that rectangle has a length and a width. Has a length and a width. So what we're trying to do is maximize the area of the rectangle. So we're looking to maximize area, which we know to be x times y. So what do we know from our previous studies in calculus? We know that when we're looking to maximize something, when we're looking to find the largest value of a function, it happens at the critical points where the derivative is 0, or it happens at the end points of an interval. We don't really have an interval, but we kind of do, and we don't really know how to take the derivative of something with 2 variables in it. So we're a little bit nervous, and lucky for us, there's a piece of information that bails us out. There is 120 feet of fencing. So because there is 120 feet of fencing, we know that 2x plus 2y is 120. This is what we call a constraint. And that means that x plus y is equal to 60. Hope that arithmetic isn't too bad. Which means that we know what y is in terms of x. Y is 60 minus x. So what does that mean? Well, that means that we're looking to maximize x times 60 minus x. The area function is 60x minus x squared. Well, that's something that's a little bit easier for us to talk about. It's got 1 variable, not 2. So in the whole business of, oh, I remember how to find a max, you take a derivative, set it equal to 0, and solve, this is a little bit better. The endpoints of the interval. So what's the biggest that x could possibly be? What's the smallest that x could possibly be? Well, clearly, x is not going to be smaller than 0. But what's the biggest x could possibly be? Well, there's 120 feet of fencing, and there are 2 x dimensions. There's this fence and that fence. So if they both take all 120 feet of fencing, then they're both 60 feet. So we're going to say that x is somewhere between 0 and 60. That's our interval. So we're going to run the exact same process we've run before. We're going to maximize this function subject to that interval. If this has a max, it happens either at 0 or at 60 or at some critical point between 0 and 60 where the derivative is 0 or does not exist. So now we do the calculus thing. We take the derivative, that's 60 minus 2x, and we ask ourselves when a double prime is 0. Well, it doesn't take too long to set this equal to 0 and solve. Turns out that x happens to be 30. And so you say, well, the answer is 30. And I say, hang on a second. Hang on a second. Here's our number line. 0 over there, 60 over there, 30 over there. 30 is a critical point. X equals 30 is a critical point. At x equals 30, there could be a max, there could be a min. So take a look at the derivative on either side. 60 minus 2x in this interval is positive, and 60 minus 2x in this interval is negative. So let's see what happened. Well, a prime changes from positive to negative at x equals 30. Yes, first derivative test tells me if a prime changes from positive to negative, then a changes from increasing to decreasing. That's a max. So let's answer the question. Question is, what are the dimensions of the pen of largest area? Well, x turns out to be 30. Y turns out to be 60 minus 30. That's 30. So we answer the question. The pen of largest area is 30 feet by 30 feet. That's the key. We answer the question based on calculus, based on an analysis of the derivative on an interval we've chosen. The pen of largest area is 30 feet by 30 feet. So I'd like to complicate the matter just a little bit. Farmer Brown has the same 120 feet of fencing, but we're going to put a fence in the middle. I don't know why we're going to put a fence in the middle, but we're going to put a fence in the middle. And this whole dimension is going to be x, and that's a y, and that's a y, and that's a y. Wishes to enclose a rectangular pen of largest area. What are the dimensions of the pen? Well, we can do this. Uh, Again, we're looking to maximize area. So we're looking to maximize the area of the pen, which is length times width. But you're thinking, I don't know how to take the derivative of something with two variables in it. Well, that's true. You don't. So let's look and see if there's a constraint that can help us. The constraint is that there are 120 feet of fencing, which means that 2x's plus 3y's is 120. And that means that 3y is equal to 120 minus 2x, and that means that 1y is 40 minus 2/3 x. And so that means that the area function is x times 40 minus 2/3 x. The area function is 40x minus 2/3 x squared. This is the thing we are looking to maximize. On what interval? Well, that's a good question too. There are lots of y's. If all of the y's took up all of the fencing, well, they would all be 40, but y is not our variable, x is our variable. There are still two x dimensions, and if the two x dimensions took up all the 120 feet of fencing, we are still looking at an interval from 0 to 60. We are still looking at that. So we're going to take the derivative, and we're going to see when that derivative equals 0. Because if this function is going to have a max on this closed interval, it's going to happen at 0 or at 60 or at some place in between 0 and 60 where the derivative is 0 or the derivative does not exist. So the question is, when is that 0? Well, algebra. Ooh, algebra. 40 equals 4/3 x. X is 30? X is 30. So what does that tell us? Here's our number line. It's a number line for a prime. On 0 to 30, the derivative is positive. On 30 to 60, the derivative is negative. So a prime changes from positive to negative at 30. So x equals 30 is where a max occurs. The max does not occur at 0. Function increases on 0 to 30. The max is not at 60. Function decreases between 30 and 60. So what are the dimensions of the pen? Well, the pen of largest area measures 30 feet by, let's see, so take that 30, substitute there 20 feet. Those are the dimensions of the pen of largest area. So the process in both cases is the same. We have a function that we want to maximize. The function has two variables. We want to eliminate one of the variables. We do so with a constraint. We identify our interval so that we can do the thing we've done before. Take a derivative, set it equal to 0, solve, check to see that it is in fact a max, and then answer the question. This is a completely different kind of question. A box is formed by cutting congruent squares out of an 8.5 by 11 piece of cardboard and folding up the sides. So you can imagine that this is 8.5 inches and this is 11 inches, and you're going to fold up the sides, make yourself a box. And all the squares we cut out are congruent, so that's all X's all over the place. Those are all congruent squares. What are the dimensions of the box with maximum volume? Dimensions of the box with maximum volume. So what are we looking to maximize? We're looking to maximize volume, which is length times width times height. Length times width times height. Can it be done? Sure. We just have to remember what we mean by length and width and height. So the length of the box, well, this is the length of the box. How long is it? Well, the whole thing is 11, but there's an x that got lost here and an x that got lost here. This is 11 minus 2x. What's the width of the box? Well, the width of the box is this dimension, and the width of the box appears to be the whole 8.5, but with an x gone and an x gone. And then the height of the box, well, this is the part that folds up. This is the height of the box. So the volume, that's 11 minus 2x times 8.5 minus 2x times x. So there is no constraint aside from the fact that it is the paper. The paper helped us to see what this is and what this is. What's the interval? Well, how far can we cut before we're in trouble? We can cut from this direction all the way down to halfway, because then we got to cut up halfway. So the biggest x can be, in theory, is halfway up this way. The biggest x can be is 4.25. So we have some function. If you're interested in seeing things look nicer, and by nicer we mean 2 sets of brackets rather than 3 sets of brackets, that's the volume function. We're looking to maximize this function on that interval. How can we do that? Well, we would take a derivative, set it equal to 0, and solve. This is a product, so how do we take the derivative of a product? First times derivative second plus second times derivative first. And then we would set that equal to 0. Well, how do we set that equal to 0? Well, we take our calculator, put this into y1, and we figure out where the zeros are. And if we do that, then x turns out to be 1.585. And I mean, you can totally pause the video, put that in a Y1, find a 0, make sure you can get that number, because that number matters. If you do a V prime check on 0 to 4.25, oh, that's not even a number, 4.25, you find out that on the left side of 1.585, the derivative is positive, and on the right side of 1.585, the derivative is negative. V prime changes from positive to negative, so V changes from increasing to decreasing. This is where the max occurs. What are the dimensions of maximum value? The dimensions of the box of maximum volume, well, they are whatever happens when this is X is X is X. So you would answer the question, the box with maximum value has whatever length this is, whatever width this is, whatever height that is. One more. A cylindrical can of soda is to hold 370 milliliters. By the way, milliliters are cubic centimeters. Find the dimensions of the can with the least surface area. The dimensions of the can with least surface area. Surface area, we're looking to minimize surface area. Surface area, there's a top and a bottom, and then there's this lateral surface here, this sort of a label to the can, and that if you unroll it is basically a rectangle. It's a rectangle whose length is this circumference and whose height is this height. So if you're drawing at home, that's radius, that's height. We're looking to minimize the surface area. That's 2 pi r squared plus 2 pi rh. Here we do have a constraint. And the constraint is that the volume has to be 370. The volume has to be 370. How do we find volume? It's pi r squared times the height. So if I'm looking to eliminate that h, it's doable. So the surface area is 2 pi r squared plus 2 pi r h. So the surface area is 2 pi r squared plus 740 over r. On what interval? Well, basically, r could be 0 essentially, or r could be pretty much anything you want. The bigger r gets, the smaller h gets, but in theory, r can be as big as we like. So we're going to take a derivative. You should make sure that you know why that is so. We're going to find out when s prime is 0. If we do that, either by algebra or by the machine, r turns out to be 3.891 centimeters. And if we were to run an analysis, here's s prime, 3.891, we would find out that on the left side of 3.891, this derivative is negative, and on the right side of 3.891, this derivative is positive. S prime changes from negative to positive, which means S changes from decreasing to increasing, which means this is a min. And so the minimum surface area occurs when r is 3.891 centimeters, and oddly enough, that makes the height twice that. That's worth thinking about. We've gone on long enough. When we get into class, we'll break down how this works, do a couple of these ourselves, see if we can get a handle on it. I'll see you there.